Good afternoon to all colleagues. My name is Zlata Tošić. I come from Technical University Dresden, and together with my colleague Martin Eichenauer, will present our today's paper. As engineers, we should be aware that the report of United Nations Environment Programme from year 2020 states that the portion of the building construction sector is total 35% of energy and 38% of the emission of process-related carbon dioxide emissions, and 10% of which are actually manufacturing building materials such as concrete. What can we do about it? Well, we can start to use more recycling materials in the construction to spread awareness, and also build with more control and more precision and affordable if it's possible. What is our solution? One solution can be prefabricated in building industry, and our topic are concrete freeform shell structures. As you know, the conventional building system has a lot of downsides, such as high costs, formwork, and very time consuming. And with using geometrical methods for surface analysis and optimization, combined with contemporary technology of 3D concrete printing without formwork, as a result, we want to deliver fabricated concrete models that can be used for assembling the structures. How do we do this? We chose for the design the pavilions complex, starting with the shape bases, openings with the defined arcs, and based on the calculation of the membranes in Caramba, for Grasshopper, we got minimal surfaces for finer design. Based on the top-down design approach, we wanted to evaluate the potential of the starting design by comparing the geometry and the structural properties that can be seen. Here, directions of the principal stress and curvature are very close, which give us a sign that there is a good potential for PQ mesh subdivision and cross-section material optimization within the edges of the PQ meshes. Now, what are the production conditions for prefabrication? They're based mostly on the geometrical limitations, such as planarity, as a consequence of the material disposition of the flat platform, then scalability and adaptability, meaning the variance in size and shape, and no geometry torsion, meaning the flat connections between the side elements, which is one of the biggest challenges when it comes to freeform shell structures. Our algorithm presents bottom-up approach of PQ mesh generation, starting with two inputted curves and the number of elements, based on number of the elements and circular mesh system properties. The algorithm generates PQ mesh system with a tendency to fulfill the previous mentioned prefabrication conditions for every model. Looking at the shell design and the boundary vertical arcs, you can see that they're supposed to cut this part in order to get the final design. And here in the small detail, you can see the principle of no geometric torsion.
In the next step, we tested whether a better structural performance of the shell can be achieved by slightly manipulating the shape. The PQ measures are completely defined by 6 arcs. So we only vary the parameters that define the arcs, not wanting to influence the original architectural concept too much. The supports are fixed against displacement, and the forces applied are wind, snow, and dead loads. Our criteria of optimization were minimum deformation and utilization, as well as similar geometric parameters of the modules, and compliance with the conditions for prefabrication. Since it is an optimization with several target variables, one has to choose from several results. We choose the variant with a lower utilization to keep the weight of the modules particularly low. As the next step, we optimize the cross-section of the individual models. For this purpose, the dimension of the edges was determined, and in an algorithm we developed, the inner part was strengthened in a loop until the utilization is below 100%. For practical reasons, the inner part is at least 1.5 centimeters thick. The largest thickness needed is 3 centimeters. The material thickness corresponds in large parts with the utilization of the modules. The next slide shows the final construction. The triangles are created by the fact that the square modules do not end in one plane and therefore have to be cut at the sides. The geometrical and constructive properties are listed in the table below. The maximum deformation is 0.96 centimeters with a maximum utilization of 82% and a total weight of 21.5 tons. In summary, we can say that we have developed a method by which shells can be efficiently panelized. At the same time, the individual modules can be controlled well in terms of their shape and thus meet the requirements that 3D printing has for modules. In the future, we will additionally develop algorithms that directly include the boundary curves and that allow a more direct influence of the production conditions on the algorithm, which will allow us to contribute to the development of prefabricated shell structures. That's all from us, and thank you for your attention.